Dear students, this is our third lecture in the main memory. So over the past two lectures, we have got a glimpse of how the DRAM cells are actually organized into columns, rows, banks, ranks, DIMMs and channels. And we also looked at the memory controller, and we we were trying to understand the various jobs or what all different components the memory controller has. We looked at the address mapping, wherein the physical address is divided into the column, row, bank, rank, dim and channel numbers, and then the address, the request is enqueued either in the read queue or write queue. At this juncture, there can be some request scheduling that can be done by the memory controller based on some priorities. Following that, we looked at various DRAM timings that we need to obey to write or read the data from the DRAM. All these timings need to be closely monitored and adhered to, and the memory controller does that job. Following that, we looked at what's called the page table, which basically gives the information about what all rows are open in the banks of the DRAM. Accordingly, the memory controller will decide to insert the appropriate DRAM commands. If it's a page hit, it inserts a cache into the command queue. If it's a page empty, it inserts an act followed by a cache. And if it's a page miss, then we need to insert a pre followed by an act and then a cache. Now let's move on. A quick recap of the working of refresh process in the DRAM bank. The memory controller, which is on chip, occasionally sends a refresh command to the DRAM device. The refresh controller, which is on the DRAM device, takes over the operation of this device, and within the DRAM device, it issues back-to-back activates, wherein a particular row is selected and read into the row buffer, and followed by a precharge, where the data is written back to the original position. Another row, activate, and a precharge. So the refresh controller will issue a sequence of activate and precharges for the rows in the banks or the sub banks of this DRAM device. Now the question is, will the refresh controller refresh all the rows in a single go, or does it have any other way of handling it? So with that, we will look at the refresh timings. The refresh related parameters are something like this. We need to refresh every DRAM cell in our main memory for every 64 milliseconds. Now, if the ambient temperature is greater than 85 degrees, then the refresh rate is doubled. It means that we need to send a refresh, or we need to refresh the DRAM cell for every 32 milliseconds now. The major downside of refresh operation is that particular rank, usually refresh happens at rank level. It means that when the memory controller sends a refresh, all the banks in that rank will undergo refresh operation. At the physical level, it means that all the DRAM devices of that rank take this refresh command, and internal refresh controller of all these devices comes into picture. Now, when the refresh controller is busy refreshing the rows, it is unavailable to the memory controller for the regular reads and writes. It means that during the refresh operation of the DRAM, you can assume that there is no main memory available to us. So whatever the cache misses are there, they will keep waiting at the memory controller for the service. So refresh operation is in a way a performance blocker, because if any of these reads are actually stalling our pipeline, now because of refresh, the number of stalls will increase. Now, touching upon the previous question, will the refresh controller refresh all the rows in a single go? Earlier that was the case, but in the modern day sub-banks, there are huge number of rows in each of them. For example, if you consider a 16 gigabit X4 DDR4 DRAM device, it has 2 power 18 rows. Now for each of these rows, if you want to send an activate and precharge internally, it takes a lot of time. So a provision has been given which is called distributed refresh, wherein we divide these 2 power 18 rows into small groups, and when the memory controller sends a refresh command to the rank, one of these groups will be refreshed at a time. Now let's try to understand it a little further. The refresh command needs to be sent by the memory controller for every TREFI interval. TREFI expands to refresh interval. It is the time between two refresh commands. Upon receiving the refresh command, each sub-bank refreshes the predefined number of rows, and the time to refresh this set of rows is TRFC. TRFC is refresh cycle time. Simply put, it is the time taken by one refresh command that is sent by the memory controller. If you look at the timeline, once a refresh command is sent to the device, it spends certain amount of time refreshing it, that is marked as the red box here, and we need to send a refresh command for every 64 milliseconds. So this was the case when the capacity of the DRAMs were low and the number of rows in the sub-banks were very few. But like I already mentioned, in distributed refresh, the rows are divided into certain groups. The number of groups is fixed, which is 8K, that is 8192 groups. Now, it means that the 2 power 18 rows in the example sub-bank we saw, it will be divided by 8192. That would come to 2 power 5 rows in each. It means 32 rows will form one group. Once we send a refresh command, the first refresh command will refresh 32 of those rows. The next refresh command refreshes the second 32 rows, third, fourth, so on and so forth. This way, in a particular 64 millisecond window, the memory controller now sends 8K refresh commands. Each refresh command will refresh the 32 rows. If we zoom into one particular interval, that is our TREFI, it is 7.8 microseconds. How did we get it? It is basically 64 milliseconds on top of 8192. For every 7.8 microseconds, the memory controller sends a refresh command and the device spends TRFC time refreshing. Now, if we want to understand how the time in terms of the percentage of time in terms of some numbers, as the device capacity increases from 1 gigabit to 32 gigabit, the amount of time we spend in refresh is increasing. So for example, for 32 gigabit device, the main memory is unavailable to us for almost 10% of the time. And this is during the normal temperature, which is below 85 degrees. Now if we consider per minute, we are sending in the sense the memory controller is sending 16 refresh commands to the device. If we consider extended temperatures, which is 85 to 95 degrees centigrade, we need to refresh at twice the rate. Accordingly, the time we spend in the refresh is increasing. For example, for the same 32 gigabit device, we spend almost 20% of the time in refresh at high temperatures. It means for every 100 seconds, 20 seconds, the main memory is not available to the core because it is busy in refresh. So in the normal temperature, we send 16 refreshes per minute, and in extended temperature, we double that number. So handling the refresh has been quite an issue because it directly impacts performance. So there were some features that were provided by the DRAM manufacturers. One of them is postponing the refresh commands. It means we can send the refresh commands for every TREFI, or we can at max wait for 9 TREFI intervals between two refresh commands. Now, how would this help? If at this particular time, if we see that the core is sending a lot of requests to the memory, instead of delaying those requests, we will delay the refreshes and by 9 intervals, and in the 10th interval, we'll send all the pending refreshes. We have delayed 9, so all the 9 will be here. And later on, we can resume our normal operation of sending one refresh command for every refresh interval. This is called postponing refresh commands. Another feature is quite opposite, wherein instead of apart from the regular one refresh command per TREFI, we can send 9 refresh commands prior, and after that, for the next 9 TREFI intervals, we need not refresh. But the key constraint is in a 64 millisecond window, we need to send 8K refresh commands. So there is some provision of how, if possible, we can on demand delay or prepone the refresh commands. But we need to still send 8K refresh commands in 64 milliseconds. Apart from this, there are a few other features which are temperature controlled refresh modes, self refresh, auto self refresh modes in the DRAM devices, which the memory controller can use. With all this, the memory controller tries to manage the refresh operations. We can term that as refresh management, because the refresh makes a rank unavailable for TRFC time. We need to find an opportune time to send the refresh commands. Basically, the opportune time can be defined as some possible window where the main memory utilization from the core is low. It means there are very few requests, so we can do the refresh operations during that time, so that the overall performance might not get affected significantly. So over the past decade or so, there were many refresh management techniques that have been proposed by both industry experts and academia. This is a topic for an advanced architecture course. Apart from the refresh management, The DRAM also has various power modes. Let's try to understand them. In general, it was observed that DRAM based main memory that we use in our regular laptops, mobiles and servers or enterprise systems, it contributes to 25 to 40% of overall power consumption of the system, so which is huge. So accordingly, to reduce the power consumption of DRAM, there were some power modes that were proposed and implemented in the hardware. So here we have a state diagram. I'll explain it step by step. So in the normal operation, a bank will be in active standby mode, and in active standby mode, it consumes 45 milliamperes of current. It requires that. And then if all the banks of this rank are recharged, my bad, the state diagram is per rank. So if any of the bank is in active state, it means that some row is open in one or more banks. We say that the rank is in active standby state. And if all the banks are in pre-charge state, it means that no row is open. We call that pre-charge standby. And extending that, we have a self-refresh mode wherein the DRAM has the data, but the core will not be able to access it. So the best example for self-refresh is when we put it in sleep mode. The data is still there in the DRAM, but it will not be used by the core because the core itself has been shut down. But we want the boot up to be fast, so we don't move the data from the main memory to the secondary memory, and to maintain the data we need to do the refresh. Only refresh internally will happen in self-refresh mode, and the data is not visible to the core or accessible to the core. Now when the DRAM is in active state, there are possible other state transitions which can happen based on the utilization of DRAM. There are some power down modes: active power down, pre-charge power down, pre-charge power down. Two variants, one is the fast variant, other is slow. What that's fast and slow means, if we put the rank in a pre-charge power down slow mode, it means to bring it back to the regular state, the pre-charge state, it takes longer time. In the same way, we can have a pre-charge power down mode fast, wherein we can bring back the DRAM from this mode to the regular mode a little bit fast. So if you see in the self-refresh mode, the current needed is just 6 milliamperes, whereas in complete active standby mode, we need 45 milliamperes. And in power down fast mode, it is 35. Power down slow mode, it is 12 milliamperes. So now the memory controller, being aware of these power down modes, various power down modes, if it wants to save some power, it needs to observe how the memory utilization is and accordingly move the rank into one of these states. So all the transitions across these states are the commands given to the rank from the memory controller. Here it is PDX, this is PDE, and here it is PDE, DLL off, here DLL on, so on and so forth. In the regular usage, the DRAM will always be in either of these two states. If there is some low utilization, it will be in one of these three states, and if there is no utilization, it would be put in self-refresh mode. So all these activities of refresh management and power mode management will be handled by the maintenance block in the memory controller. So apart from the refresh and power modes, in the maintenance, as part of maintenance, the memory controller also does something called as scrubbing, which will clean the data. Also it does error detection and correction. So for as part of maintenance, the memory controller monitors all the memory activity that is happening and accordingly takes a call when to send a refresh, when to put it in the low power mode or rather power down mode, or which power down mode it has to put in, and if there is any error in the data being transmitted from the DRAM to the chip, it needs to identify that and possibly correct it. Now the last task of the memory controller is DRAM command scheduling. Now if you look at this picture, we have various DRAM commands enqueued in each of these command queues. So here we have the scheduler which needs to pick one command every cycle and send it to the DRAM. So we can pick the command based on the page status of the request, or it can be based on age. It means that the oldest request will be given priority. How do we know that it's the oldest request? There will be a notion of timestamp. It can be relative, or it can be based on the criticality of the request. We have seen such a thing at the request scheduling also. The processor can send more information saying that some particular request or a set of requests are very critical to it, so that the memory controller can speed up their service. Or the priority can be based on the type of request also. The typical priority would be read over writes over another specialized request called prefetch. I haven't touched on prefetching at the caches, so you can ignore it for now. And any other command scheduling algorithm that can improve the overall performance can be deployed here. Again, over the past 10 plus years, or to be exact from 2005 onwards, wherein we moved from single core to multi-core era, from then on the main memory has been under tremendous pressure, and the memory architects and the system architects were coming up with various techniques to improve performance. So command scheduling is one of the target areas. And typically the scheduling algorithm is decided by an extensive analysis of the workloads of the target application. If we want to deploy our DRAM in, let's say, server environment, the server workloads will be analyzed. If you want to deploy our main memory in the laptop or a desktop, the workloads will be different. If it's on mobile, again the mobile workloads are different. So accordingly, the scheduling algorithm will be chosen. So that is the last job of the memory controller. With that, we have completed the overall picture of how the DRAM is organized physically and what all different aspects the memory controller needs to do to handle a request from the caches. Over the years, there have been many DRAM standards that have been productized, and Joint Electron Device Engineering Council, in short JEDEC, is a consortium of both industry and academia who take call on these standards. Now, for different needs, different standards of DRAM are available. For an bandwidth optimized setup, or for a latency optimized setup, or a power optimized setup, or the form factor can be a decision factor, or we would need a DRAM which is balanced in all of them. So for bandwidth optimized implementations, we have what's called graphics DDR, GDDR. For latency optimized, we have RDDR or RLDDR, reduced latency DDR. For power optimized, we have LPDDR. For form factor optimized, we have devices with high device width This would be critical for our mobile applications, and the balanced version of all these is the regular DDR which we use in our desktops and servers, so on. Now if you can check any mobile or any computing system which is built to be mobile, for example your tablet or a highly optimized system like a Microsoft Surface Pro or something like that, it would come with a low power DDR, because there the power consumption is mainly is a main constraint, because they are battery driven. So accordingly, based on the target deployment, we pick that DDR and use it. If we look at the balanced version, which is the regular DDR, there are many generations over the past 3 or 4 decades. It is driven again by technology scaling, that is Moore's law. So the first generation was SDRAM. S stand for synchronous DRAM. Before that, the DRAM was asynchronous. After that, they have deployed a clock, and all the later deployments of DRAM are synchronous DRAMs only. So the first generation was SDRAM, and the speed was somewhere between 100 to 166 megahertz only, and it was operating at 3.3 volt. Following that, we have the first DDR. If you look at the frequency, it has improved slightly and the operating voltage decreased a little. Then we have the second generation of DDR. The frequency almost doubled with DDR, operating voltage reduced. Then we have the third generation. The frequency improved a little and the operating voltage dropped a little. What we are currently using widely is DDR4, and the typical memory frequencies are somewhere between 1 to 2 gigahertz, and the operating voltage is 1.2 volts. DDR4, which can go up to 3.2 gigahertz and operate at 1 volt, is currently under development. We would see these DDR5 based DIMMs sometime in 2023 onwards. Now, if we look at the various DRAM parameters, which are the physical chips capacity, the cost, access time of a row and a column, and average column access time to an existing row, which is the access time of, which is basically TCAS, and this is TRCD. If you look at from over the years from 1980 to 2012, the access latency dropped from the TRCD dropped from 250 nanoseconds to 35 nanoseconds, and TCAS dropped from 150 nanoseconds to 0.8 nanoseconds, and the capacity slowly increased from meager 64 kilobit to 4 gigabit now. And with technology scaling, we have an additional advantage of cost drop, so it has become quite cheaper now. But when compared to the scaling of the processors, the scaling of DRAM was not so encouraging, and that's the reason we have the memory wall, where both the latency and bandwidth of the DRAM are bottlenecks for overall system performance. So with that, I conclude the main memory part in the memory system module, or memory, the third module of the course. You need to go through chapters 10 and 11 of Memory Systems book by Bruce Jacob. I will share both the chapters on Google Classroom. Go through them, and if you have any doubts, we can discuss. Next week, we will have 2 to 3 lectures on secondary memory. specifically flash drives, which are also called SSDs. I'll pause for now. Thank you.